So today, I'm going to present about the water pollution and membrane technology for purification. So the learning objectives for this chapter is that we hope that after attending this course, you understand minor water pollutants, the sources, and also the impacts of water pollutants, and also you can review what's the difference between conventional versus advanced purification methods. And then you can also master principles of membrane separation. And because there are a lot of types of membrane separations, yeah, there are microfiltration, ultrafiltration, nanofiltration, reverse osmosis, and so on. But I hope that you can also understand them and know the difference. And also, you can analyze or identify membrane folding, yeah, because that's like one of the challenges in membrane filtrations. And also, you understand what is the mitigation strategies that might be applied to reduce or prevent this membrane folding. Now, let's see about the water pollution. So the picture that you see here is actually the Citarum River in Bandung. Yeah, there are a lot of waste there, so you can imagine that the water is very dirty. Yeah, it's our concern in regarding this problem, especially in relation to the clean water that we need. Yeah? Um, and it's actually global water challenge because according to World Health Organization, 2.2 billion people actively manage drinking water, uh, even though, let's say, healthy drinking water is like a basic needs for human being. Yeah? And then these water scarcity also affects more than 40% of the world population. So it's quite large if you think about it, that 40% of population has this water problem. And there's also outside factor like climate change that might intensify droughts or floods, yeah? And also pollution, which reduce usable freshwater stocks. And then according here from the Statista data, there's like water stress, which is predicted by 2050. So for example here, let's say the one with brown color that is extremely high stress. But for example, here in Indonesia, it's considered medium to high, so not that urgent, so to say. We still have enough water, not in the red or even the brown color. But then, of course, when we want to prevent or supply clean water, we also want to understand what causes the shortage of it. We have water pollution, yeah. So water pollution includes any chemical, physical, or biological change in water quality that harms living organisms or makes water unsuitable for desired uses. Yeah? So not only for human being, but for other organism that needs water. And then the sources of these water pollutions in general is divided into two. So the first one is coming from a single place, yeah, such as industrial discharge or sewage outfall. That's, you can find out like what is the source. And then the other one is the non-point sources. So it could be from anywhere, such as agriculture runoff or urban stormwater. And then these water pollution will then, for example, pollute the groundwater flow over here, yeah, or maybe seawater and so on. Yeah, that makes the water not healthy anymore for human or for organisms. And these water pollutants are divided into different classes. Yeah, so just to make us easier to identify like which type of these pollutants belong to. So we have pathogens, yeah, making us sick, for example, like bacteria, viruses, or protozoa. And there's also organic matter. They can be biodegradable organic substances, yeah, which relates to the biological oxygen demand. And there is also like refractory, like humic acid or synthetic organics. There's also nutrients, yeah, elements such as nitrogen, phosphorus, which can cause eutrophication. So, for example, nitrogen comes from fertilizers in food agriculture field. And there are also heavy metals, yeah, lead, mercury, cadmium, arsenic, or chromium. Those are not healthy for us or for other microorganisms. Of course, there's like a limit in which we consider unhealthy, but if we can get rid of them, that's even better. Yeah? And there is also salt, of course. If there's too much salt, then it's not healthy. Yeah, and then the amount of them is quantified in TDS or total dissolved solids, or sometimes it is in hardness. For example, if you have water with a lot of calcium ion or magnesium ion, that is also not good for drinking water or even for washing clothes. Yeah, and also there are emerging contaminants. Yeah, this mostly the reason. So it's not let's say in nature, but it's because human activities. It could be from pharmaceuticals, yeah, or personal care products, like when we are using a shampoo or bath surfactants and so on. Yeah? And there is also PFS or per and polyfluoroalkyl substances, and there are also like reason that we are also concerned about. There's also microplastics. Yeah? So these are the classes of water pollutants. So you can imagine there are many of them, but we can classify these into the similar characteristic, yeah, from the point of physical chemical properties. So, what are the impacts of water pollution? Why are we concerned about this water pollution? I mean, if you're living in a good city with a good water processing water sources, you might not have problem with this, yeah. But if you are near factory, for example, or if you are in an area without good water processing, or even let's say the area doesn't have water sources, then it might be more high impact for them. But in general, this water pollution, of course, has health impacts. Yeah, we don't want to be sick because of consuming unhealthy water. But probably some contain carcinogenic chemicals like benzene or others, or heavy metal poisoning, yeah? Or some probably um, influence endocrine disruption, the hormone in our body. We also don't want that. Yeah, we don't want to be sick because of unhealthy water. And there's also like impact to the environmental area, such as if there's an area in which it is low in oxygen, aquatic life cannot survive. We call that the dead zones. Yeah? And then it might cause biodiversity loss. Yeah, maybe some of the species already not present again, and could be habitat degradation. And these also, the water pollutants might be consumed by other organisms. And then this, for example, maybe we eat fish in which this fish eat the water pollutant. And we also don't want that, yeah. And of course, these problems also cause economic impacts, yeah? Because you might imagine that if a lot of people consume unhealthy water, then there might be problem with healthcare. Yeah? Um, if the demand is too high and then the facility is limited, then you might imagine that there might be increase in healthcare costs. Yeah? Um, and then if it is influencing affecting the water, seawater, and it might also reduce healthy fisheries and aquaculture. And also it can cause a lot of money, yeah, for treatment and remediation expenses. For example, if the area, if the city has a budget for, I don't know, education, for example, but let's say they have immediate problem with water because people needs to live, needs to, consume good water, then probably this budget is then allocated for that. So it can affect other human activities when we have problem with water. Yeah? And then those can also reduce productivity and then income or on in general consequences. Let's say it might cause poor public health. We don't want that, or ecosystem degradation, food insecurity, or even economic burden. And then that might influence and then reduce the quality of life. Yeah, it's making the city or the area unhealthy place to live. Yeah? Um, and then for the water itself, yeah, there are several standards which uh, state or quantify deem as healthy water. Um, so there are physical characteristics. For example, the turbidity unit, the volumetric turbidity unit. It's a cloudiness of the water. You want to have like colorless clean water. So if you see something turbid, cloudy, then you might, suspicious of it, yeah, whether it is healthy or not. And there is also like total suspended solid. So water is supposed to be water, so it should not contain any solids in it. And of course, the color also should be colorless, and the temperature should be normal temperature, room temperature. Yeah. There is also like chemical characteristic of the water, like pH, yeah, or the number of dissolved oxygen or biological oxygen demand, or especially BOD5, yeah, after 5 days. And there's also COD, chemical oxygen demand, and so on. There's several things that the expert considered. It should be like the standard of healthy water. And there's also biological number, like the total coliform for E. coli or other viruses. Yeah? There's like, a certain number that we still can consider them healthy. Yeah. Um, so for example, there's are also like heavy metals in there might be present in water, and these are the standards, several standards. Yeah, it's in milligram per liter, and it's the concentration that is still let's say considered like the highest that it's allowed in drinking water. While for the pH, for example, the WHO considered this pH as normal. Yeah, so if you probably have pH paper and then you want to probably check your drinking water, then if it is around 6.5 to 8.5, that's considered normal. And for the turbidity, the cloudiness, yeah, it's should be less than 5, and total dissolved solid should be this amount, and so on. Yeah? It's so they have this standard when we want to consider our drinking water healthy. Yeah. Now, in treating the water, yeah, there is this paradigm that we have to consider. So the first is that we have to have or we have to protect the source. Yeah. And then when we consider the physical or chemical treatment and also disinfection, then it should be also consider the safe distribution. And then for the conventional surface water treatment, such as involving coagulation, yeah. So whatever inside the water is coagulated, and they will form sedimentation, for example, and then there might be filtered using filtration. Yeah, these are using some several type of stones, and there is also disinfection. And then after this water is checked, yeah, according to the standard, then it can be considered drinking water. Um, of course, there is also a limitation in this, such as poor removal of dissolved salts Why? Because you can imagine that the size of the salt is very small compared to, let's say, this one here, the coagulated particles that even our eyes can see. But then the dissolved salts is very small. We don't see this in water. Um, and then some probably trace of organics or maybe even small viruses might be still present in water. So if that is the case, then we need a very advanced studies to separate these water pollutants from the water, yeah, because we want to make sure that whatever we consume is healthy, yeah. Now if we see the conventional water purification, and then you will see that we need the membrane, yeah. So the conventional treatment, the step is like removing particles, microorganisms, or some colloids, and so the point is that we want to reduce the turbidity, yeah. Um, But then there might be insufficient for dissolved ions because it's too small, it's hard to precipitate, and there are probably some small organic molecules such as pesticides from the agricultural area or pharmaceuticals that might be dissolved in water. That's probably hard to remove, yeah, using conventional treatment because we see, for example, here this is the intake, for example, from water sources. Could be river, lake, or reservoir. Yeah. And we might screen them, and then here, yeah, you have the press screening, the aeration, and also the coagulation, sedimentation. So you want them, to separate, and then filter them out, and then you have like the safe drinking water. That's the conventional treatment. Yeah. But of course, there's like a limitation for this method, such as the colloidal and dissolved contaminants might slip through, or some other these byproducts like trihalomethanes or haloacetic acid or natural organic matter, which probably are still present in the drinking water. And then this conventional method might not be suitable if it is for desalination, yeah, like seawater or brackish water. Brackish water is, having salinity between freshwater and seawater. And there are also like emerging contaminants, yeah, from pharmaceutical, which might be classified as the endocrine disrupting chemicals or EDCs, or probably some antibiotics. And if it is using the conventional process, then the removal is probably less than 20%. Yeah. So you can imagine that there's still, let's say, around 80% of those contaminants, which are probably harmful for our body, which might disrupt the hormonal work in our body. And we don't want that. Yeah. And then if we compare the size, for example, if we see this is the same of human hair, yeah, so the width is around 17 micrometer, and then if we compare to, let's say, red blood cells in our body, uh, it's around 7.5 micrometer. But then if we go to a smaller size, such as a virus, for example, that is around 20 nanometer, and then if we go to dissolved salts, it's even less. It's even like less than 1 nanometer. So these dissolved salts or a virus might still be present in the water if you are using conventional method. So that comes a question. So how do we filter out pollutants that are 10,000 times smaller than a human hair? Yeah. So that's why that we discussed the membrane technology as a solution for that. So in this case, the membrane is a selective barrier. So it's a semi-permeable that allows certain species to pass while retaining others under a driving force. So you might notice that it's selective. It should be selective, yeah. But there's still like should be like a driving force which causes the movement of whatever substances between these membranes. And then the advantage of using membrane is, of course, due to its high selectivity, and it can undergo continuous operation, can be modular, and it can be also chemical-free separation potential and with lower footprint of carbon. And then they can also take up particles, yeah, especially small particles, pathogens, the viruses, or small organic molecules, and even salts. Yeah, if we are using a very small size pores of membrane, so it's quite good method. And then historically, we have some improvement or development of this membrane technology, yeah, from the osmosis, reverse osmosis, asymmetric membrane, and also now recently we have the composites of, let's say, polyamide-based membranes or microfiltration or ultrafiltration. So it's emerging. Yeah, it's good to know there are people who want to work with this technology, with this membrane technology, because it is very important for us humans to have a healthy drinking water. Yeah. So now let's take a look at the membrane science. Yeah. So in membrane, there are several things that might, I mean, you should be familiar with it. Yeah. So the first one is, as I called, a feed solution. So it's an influence solution. It's let's say the initial solution that you want to treat. For example, unhealthy drinking water contain water pollutants. So that's the feed solution that we refer to. Yeah. Um, and then we also have permeate, that is material passing through. That's basically, if we are talking about the water purification, then the permeate is the healthy drinking water that we want. Yeah. And there is also retentate or concentrate, that is the retained material. So these are the particles that are not passing through the membrane. So, for example, the water pollutants that we want to get rid of them, then they are called the retentate or the concentrate. Yeah. And then there's also the term flux. Yeah, it's a volumetric permeate flow per unit membrane area. So it's liters meter square per meter square per hour. So LMH. Yeah. Um, and this is the formula. Yeah. So it is calculated. The flux is calculated by knowing the volume of the permeate, and then we divide it by the A. That is the specific area of the membrane, the effective area of the surface of the membrane, and then T, that is the time, it's an hour, yeah. So you can calculate the flux of the permeate. So basically, you want to have a high flux because that means the separation process is quite short, it's effective. So you want to have a high flux. And there is also a membrane permeability. So it is calculated as the flux divided by the delta P. So the delta P is the difference in pressure. It could be the applied pressure and also the difference of it with the osmotic pressure itself. Because we are using, for example, water and some solutes in it. So there might be osmotic pressure. So then we can think whether like how how big is the pressure that we should apply to the filtration process. And there is also rejection here. It's calculated as 1 minus Cp, that is the concentration of the permeate, and then Cf, that is the concentration of the feed solution, times 100%. And you actually want to have a higher rejection, because that means that the membrane works very well in rejecting, for example, in this case, the water pollutants. And there's also recovery. Yeah, it's a QP over QF. So it's a permeate flow rate, yeah, divided by the feed flow rate times 100%. And then in the membrane science itself, there are two types of flow that you might want to take or to keep in mind. So the first one is a dead end, means that the flow is going down. So it's like um, perpendicular to the membrane. Yeah. So you can see that this one is the feed, and this one here is the permeate, and this one is the membrane. And when we call this a dead end, it's like one way. Yeah. So it is appropriate if we are talking about small scale filtration, because the problem is that If it is a dead end, then you might, or you can think that there might be some concentrate above the membrane, which might hinder the future filtration. So you might want to replace the membrane quite often. It can also reduce the flux over time due to the presence of this material on top of the membrane. There is also what we call as a cross flow, and then you can see that the cross flow is actually, flowing in parallel of the membrane. Um, so why is it like this? Basically, the idea was to, removing whatever on top of this. So you want to remove this by applying pressure parallel to the membrane. And then you might think, okay, so how about the permeate that we want? I mean, there's a permeate that comes to a passing through the membrane because one of the reason why the particle moves from one area to the other through the membrane is, for example, due to the difference in concentration or probably the difference in pressure. Could be the reason. But of course, if we apply the same flow, you might imagine that for this one we have like a lower flux, yeah, compared to this one, but uh, we can maintain a more, like longer shelf life of the membranes. Like we don't need to replace it often because this makes sure that the accumulation of the particles above the membrane is not too much. So there's like, advantage and disadvantage of these two types of flow in the membrane filtration. And there's also like membrane classification by pore size, and this is very important because the idea of using membrane is because we know that membrane has, it's a pore size, typical pore size. We call that like MWCO, like the molecular weight cutoff. That is like the maximum size of the molecular weight that can pass through the membrane. So if you, for example, buying a membrane for, I don't know, filtration in your lab, for example, you might also consider like what is the molecular weight cutoff that you need for your filtration because I mean that depends on what you want to separate. So then the membrane is classified by pore size. So the first one is microfiltrations, and you can see that the pore size is between zero point 0.1 to 10 micrometer. It can retain suspended solids, large colloids, bacteria, and also some algae. Yeah. And then this microfiltration operates at low pressure and it actually has the highest flow rate among the four types. So we have four types of this classification. The second one is the ultrafiltration. Its size becomes smaller, so it's from 0.01 to zero point 0.1 micrometer. And the in MWCO here is around 1,000 to 500,000 Daltons. That is, so if I say 1,000 Dalton, it means it's 1,000 gram per mole. Right? So 1 Dalton is 1 gram per mole. Um, it can retain proteins, viruses, and larger organic molecules. But then it requires moderate pressure while allowing water and small minerals to pass through. Yeah. So this is the schematic representation for the filtration membranes. Yeah. And then the third one here is the nanofiltrations. Its pore size is even smaller, and then the molecular weight cutoff is even smaller. It's around 200 to 1,000 Daltons. So you can imagine like small organic molecules between 200 gram per mole and 1,000 gram per mole can be filtered out. It can contain sugars, dyes, multivalent ions, and so on. Yeah. But then they operate at intermediate pressures, and it can block organic matter while letting some monovalent salts pass. There is also reverse osmosis. Yeah, so the reverse osmosis has even smaller size. It's less than 0.0001 micrometer. So less than 10 nanometer. Yeah, so it's virtually all dissolved in organic minerals monovalent salts like sodium and chloride, and very small organics. It can be filtered out. Um, and because of their small size, very small size, they are actually the tightest membranes available. Yeah. But because the size is very small, then you can imagine that you need a very high pressure to operate this kind of membrane. Yeah. So because I mean you want to overcome the natural osmotic pressure to produce highly purified water. Now, how about the membrane materials? Yeah. If you want to make a membrane material, what chemicals should we use? Yeah. So in general, there is what we call as polymeric organic membranes. Yeah. For example, here we have polysulfone or polyether sulfone. Uh, they are largely used because of the exceptional thermal stability. It also has wide pH tolerance, and it's a standard choice for ultrafiltration and microfiltration. Yeah. And there is also another type, which is a polyphenylidene fluoride or PVDF. It is very famous for its high chemical resistance due to the presence of the fluorine over here. Yeah? So it's, for example, this is also Teflon with four apps. But then we have like two, which is PVDF. So the presence of the app is actually causing it to be resistant to chemicals. Yeah. And we also have polyacrylonitrile or PAN, which is highly hydrophilic, which attracting water, and it has extremely resistant to fouling by oils and organics, and it is commonly used in industrial wastewater. We also have PTFA. Yeah, it's highly hydrophobic, which repels water, and then it inert to almost all chemicals due to the presence of four fluorines in the structure. And it is ideal for membrane distillation and some aggressive acids or solvent filtration. So it really depends on what types of substance inside the feed water, the feed solution that you want to filter it off. And then there is also cellulose acetate. Yeah, it's a biodegradable polymer with a low fouling tendency, high water flux due to the hydrophilic structure, and it's biocompatible, but it is susceptible to biological degradation because of the structure. You have glycosidic linkage of this or alkoxy linkage. Um, and if there's like some microbes or fungi or something like that, and it can break down this linkage, then you're not having a working membrane anymore. And it's also limited to a narrow pH range, which is not suitable if you have um, feed water with a very high pH or low pH. And we also have polyamide. Yeah, it's a industry standard for nano filtrations. It has this general structure over here. Of course, if you are seeing this structure as a chemist, you might also think that it's just a basic structure. So, for example, if a company sells you polysulfone membrane, and let's say you find that they have like a very outstanding performance compared to a normal polysulfone that you buy from other company, for example, then there might be other structure inside the membrane. That's normal. I mean, uh, in industry, I don't think you are um, it's mandatory to really tell you what's in the product. We in our academic environment, for example, we are always told to really involve whatever we find. Yeah, for example, when you are doing research in your laboratory and have the data, we have an obligation to report whatever we have especially since, for example, if we are in a public university, we are funded by the government, or we have research grant from the government or from the community, then we kind of have to report it. But then if you are talking about industry, then they might have a certain secret. So of course you should not be, for example, too surprised if that is, let's say, the same type of membrane, like, oh, this is polyphenylidene fluoride membrane, but then they have like a very specific or a very high performance or properties, then they might modify it. And I think it's actually like your jobs as chemists to work on that, because you do know the structure, you can modify them according to the needed applications. Yeah. And we also have the polypropylene, yeah, polyethylene, even though they are used in plastics, for example. But sometimes they are also used in membrane, yeah, because it's very low cost due to um, the production cost. Like they are very mature in production, so it's a very low cost, and they also has a very high mechanic properties, and they can be used for coarse microfiltration and blood oxygenators. So you can see that different structures, different materials might be used for different applications. Yeah. And there is also a ceramic and inorganic membrane. So the first one is a polymeric membrane, that's the organic membrane. But this one here is the ceramic or inorganic membrane. So let's say, I don't want to work with organic material. I want to work with something inorganic. I want to work with the composites. Then there is also this ceramic and inorganic materials, yeah, such as using alumina, because it's highly durable with excellent temperature resistance, and some also using titanium oxide here, which is highly hydrophilic, and it can resist organic fouling. Yeah. And they also have the photocatalytic properties, which might help break down the pollutants on the UV light. Yeah. So you can also see that the circumstances where the membrane will be used also might influence the design of the material that you are going to choose in making a membrane. Because let's say, it's in open condition, like open to atmospheric, open to, you also have like UV, and you might also think maybe you need something to add in which it can use the photochemistry reaction. Yeah? There is also zirconia. Yeah. So not only in synthetic gyms, yeah, it's also used in membrane materials which is extremely stable at the high pH levels, and sometimes it is used as a fine coating over alumina supports. And then there's also silicon carbide with highest flux rates among ceramics, and it has like extreme chemicals and thermal robustness, but it is highly expensive. But don't worry, expensive or not, it actually depends on who will buy it. Like, it doesn't matter if it is expensive if you can buy it, because even if it is cheap, if you cannot buy it, why does it matter? So it's not the problem. Like, as long as there's like a buyer, like a market of it, even though the membrane is very expensive, if the human needs it, they will buy it, especially if it relates to the medicine health, for example, because human wants to live long. And then there's also thin film composites. So now even they want to combine the organic materials with inorganic materials, because we do know that when we combine them, we might have a composition in which they are compatible one another, and they can produce a very strong or superior characteristic compared to their precursors. Yeah? Now, these thin films is around 100 to 200 nanometers, so very thin. And sometimes it is used on a porous support, yeah, with supreme film selectivity. And then if you see, so this is the same picture of a thin film composite membranes. Yeah, it's using polyacrylonitrile as a support. So this is sorry, this is the same here. Yeah, so you can see the surface, the morphology. This is the bottom surface, and this is the top. And you can see that this is like a layers, let's say from the composite with the polyacrylonitrile. So the membrane morphology itself is divided into two uh, types. Yeah? The first one is symmetric, and the second one is asymmetric. So the symmetric one here can be dense or homogeneous, like this one. This is the cross section of the membrane. They can be porous or cylindrical, like this. When you say about symmetric, it doesn't mean that the size of this like the same, but you know, like you have like pore there and you have like pore there. So you have like these symmetric as in, you know, like there's like pore on top or on the bottom. And there is also porous or sponge like. So this is let's say this is porous. So I would imagine if there is like a permeate going, it's something like this. For example, blah 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 blah, and then going. See this one, that one, and for example, this one coming, this one or this one. This is what we call as symmetric. Yeah. And then for the asymmetric, you can see that, for example, this, you have porous top layer. So you have a distinctive, like different type of combination. So this one is like very dense, but this one you have like, you know, a more inhomogeneous structure. And it can also integrally skin or densified top layer, something like this, and also become composite with densified top layer. But anyway, you see the difference. So it's like you have like two types uh, at least. Yeah. So the first one is dense, but then the second one you have something like this or like this. So you can see the difference between symmetric and asymmetric types of membrane morphology. Now, for the symmetric membranes, yeah, so they have uniform structure throughout their entire thickness, and then they have the resistance of the mass transfer should be identical across any plane of the membrane. For example, if it is a dense symmetric film, it could be in the form of a solid polymers without visible pores. I mean, like our eye doesn't see it, but it's there because, for example, in the smaller size of pores. And then the transport might occur via molecular diffusion, and they are primarily used in gas separation and perforation, or something even smaller. And there's also like porous symmetric membranes, which, you know, they have uniform for distribution from the top surface to the bottom, and they are commonly used in microfiltration, where all the filtered particles are trapped inside or on top of a uniform mesh. Yeah? And then the second one is the asymmetric membranes. Yeah. So it features a structural gradient across their thickness, and they are engineered to maximize the water flow, the flux, but maintaining the high separation efficiency because you want to also have a high ejection value. Um, and the type that is integrally asymmetric membranes, such as made of a single material, but formed with a very thin or dense top skin layer with the size of, let's say, zero point 0.1 to 1 micrometer, and it is supported by a highly porous thick sublayer. So we have like two types. And then the skin detects the separation, while the porous sublayer provides mechanical strength within with the minimal flow resistance. Yeah. So let's say the first layer over here, yeah, dictates the separation. You want to separate whatever in the feed, and you want to have only the permeate. But then you want here the second, let's say the second layer, you want to have like a high flux because the separation is already done by the top layer, and you just want to, you know, having like a high flux of, for example, the water. And there is also the composite and the thin film composite membranes, which is made of the chemically distinct layers. So, for example, a highly specialized ultra-thin polymer skin layer is synthesized on top of a different porous support layer. For example, using polysulfone ultrafiltration membrane, and it could be like a really covalent bonding. So it's really chemistry. You have the surface, you have a functional group. You are using that functional group to attach other polymer on top of it. And it's used in nanofiltrations and also reverse osmosis because each layer can be optimized independently. Now we see the SAM of it. This is a very nice one. So if you're working with the membrane, like you're making a film, like thin membrane, and you want to like characterize, okay, what do I have here? Do I have a symmetric membrane or do I have an asymmetric membrane? Then of course what you want to see is actually the cross section. You know, for example, I have a thin layer over here. Now, if I see it from top of this, so I see the surface, okay? So let's say uh, something like this. This is the surface. But then what you want is actually this one. I mean, it's like a very thin film, but you want to actually have, you know, knowing that, like look at that, because you want to determine whether you symmetric or asymmetric uh, type. Yeah. So what you should do? So you are going to freeze this thin film of membrane by immersing it in a liquid nitrogen. Yeah. So you should have a liquid nitrogen in your lab, and then you immerse it. Now you will have, for example, at the beginning you have a soft, flexible, thin film of membrane, but then after it is immersed in liquid nitrogen, you will have a stiff membrane. And then after that, you kind of, like divided it. Yeah, so you kind of, let's say, cross something like that. So now you are going to check this one. And for example, this is the cross section. So it's a rather porous, yeah, but it's asymmetric. So if so this is actually the thickness. Suppose I have the thickness. I'm just making it up. I don't know. So this is 1 micrometer. So I'm just making it up. Let's say the thickness is, I don't know, 50 micrometer, or let's say 20 micrometer. So let's say this is 20 micrometer. So this is the thickness of the membrane. And so you actually see the SAM from the side for this thin film, and it's actually porous. Yeah, so it's something like that. That's actually what you want to see when you want to, decide what type of membrane that you have. And then this is the second one. Yeah, this is the asymmetric polyether sulfone membrane, and it's actually bicontinuously. So you can see that. So this is also the cross section, the thickness. This is, so you are seeing this from the side of the membrane, so not the top of the membrane, not the surface, but it's the cross section. So you can see that it has like different. So for example, you have this, but this one dense, and so on. Yeah? So you can see the difference between the symmetric and asymmetric types. So why do you want to know, or why do you care about this? Uh, because you want to explain the data, like when you are doing the flux measurements and so on. You might wonder why the flux becomes higher or why the flux becomes lower. Then you need this picture because you want to explain what is going on with your system. Um, so how this membrane is made? So there are, of course, several types of methods, yeah? But in general, we can divide it into three. So the first one is what we call as a phase inversion. This is actually, I think, the easiest one if we are doing it in, as a small scale in a laboratory. So basically, we have a polymer solution over here. We have a polymer solution, yeah, and we cast it as a vellum, on a surface, for example, on a glass surface or on a Teflon surface, and then we let it dry somehow, and then immerse it in a non-solvent bath, yeah, which is called non-solvent induced perspiration, because we want to actually making it solid. So let's say in the beginning you have polymer in solution, right? Because you dissolve it in a solvent, but then you cast it. So let's say in the beginning you have um, a clear solution, so to say, because your polymer dissolved in the solvent. And then you cast this clear solution on a surface, for example, a glass surface, then you will have a clean viscose layer. And then you immerse it in a non-solvent, then you will have a white thin film membrane, because now your membrane becomes solid, not in solution anymore, and then you will have this white color. Um, except if your polymer has aromatic group, then probably it might give colors. But then anyway, so the precipitates the polymer, creating a porous, asymmetric, or symmetric structure. And you might wonder, okay, so where does the pore comes from? It might be because the solvent leaves the polymer, or it's probably because you also add some porous agent, like porogen. You add something to make a pores in your membrane. And it should be something that is dissolved in the non-solvent. For example, if your non-solvent is water, then you might add, I don't know, polyethylene glycol, for example, in your system. So this polyethylene glycol will dissolve in water, leaving pores inside the membrane. You might also want to like play around with the size of the polyethylene glycol that you use, from the smaller or bigger and so on. Yeah? And there's also facial polymerization. So for example, here we have two reactive monomer dissolved in immiscible solvent. So basically, you are using two types of solvent, which is not miscible. So you will have an interface, and then you add two monomers, and then they will react exclusively at the liquid-liquid interface. Then it will form thin layer. Yeah? And we can call that as a thin film composite membrane. And then there is also tech etching, in which a thin polymer film is bombarded with high energy ion beams and then chemically etched, and it can create perfectly cylindrical, parallel, and uniform symmetric pores. Yeah. Now, so after you understand the principle of the membrane, you know the types, you kind of understand this uh, mode of preparation of making a membrane. Then we also want to know the transport mechanism. We want to understand what is going on with this process of filtration using membrane. So we do know that the membrane has pores, and they might have different size of pores, which, for example, suitable for microfiltration, or probably even smaller, suitable for ultrafiltration. And then the liquid and then the solute will be transport, right? And this is governed primarily by, let's say, convective flow, yeah, rather than diffusion. Now there are equations which explain this. I will not explain the equation, just to show that there is like a mathematical formula which support the theory of the transport in membrane. So the first one is the Hagen-Poiseuille equation. So it is assuming that the membrane consists of a bundle of straight cylindrical pores. Yeah? So it relates fluid velocity as a flux to the pore geometry and pressure. So it's actually similar to the viscosity, if you still remember about the Poiseuille equation. And then the second one is the Kalman-Cozen equation. So it is used if the membrane pores are highly irregular and resemble a packed bed of particles instead of perfect cylinders. So these two people proposed a new equation which actually support the finding data. I mean, if you are working with a membrane and somehow your membrane is like special type of membrane and you cannot use whatever available in the literature to explain um, the properties of the membrane itself, you might propose your own equation if it really matches your data. And then it's also a convection sieving coefficient, such as I said in microfiltration or ultrafiltration membrane because they are porous, and then if the solute are smaller than the pores, then they can be carried through by the fluid bulk movement, to do the convection. And how about if it is reverse osmosis and nanofiltration? So if the pores is very small, so it's very dense, then the mass transport is actually governed by the solution diffusion model. So it's different compared to the porous membrane where the materials flow to physical holes, permeating molecules first dissolve in the active layer of the membrane polymer and then diffuse across it individually down a chemical potential gradient. In this case, the water flux, it's the water movement, will depend on the balance between hydraulic pressure pushing the water forward and osmotic pressure pulling it backward. So you kind of, you have to go against the osmotic pressure because let's say in nature, when you have a solvent and a solute, then you will have osmotic pressure, right? So if you want to, do something reverse it, then you might need to apply hydraulic pressure. As the solid flux, then let's say the feed solution contains salt. Then the movement, the driving force of the movement is solely affected by the concentration. So it's a chemical activity gradient. Yeah? So in this case, the solute flux will be independent of the. Now, because the water flux goes up with pressure, but salt flux stays constant, then operating a reverse osmotic system at higher pressure will yield cleaner water. So this, for example, is used when you actually want to separate the water from whatever solutes inside the water. And there is also like uh, nano filtration variation, which sits between porous and non-porous mechanism. Let's say they often add electrostatic components, the extended Nernst-Planck equation, to account for the rejection of charged ion by the membrane surface charges, especially if you're using um, a membrane which has functional group, and then this functional group can produce ion, for example, based on pH. For example, if the feed water contains some acidic or basic substances, which might trigger the formation of ion on the surface of the membrane, then you might want to consider uh, the electrostatic forces. So the idea is that if you work with membrane and then you try to measure the flux of your system, the rejection of the system, and you somehow have to explain that, you can then use several equations in the literature to match your data, but you have to also consider whether your system is actually matching with the hypothesis of the equation or the theory itself. Because if it is not, if you are, I don't know, adding some other ions, or the membrane itself is adaptive to ions, then the transport in your system might be different. Yeah, and that's actually okay. I mean, that's why you are doing research. Now next, so understanding flux and the difference of pressure. Yeah. So the flux, the variable G in this case, yeah, it's go through the semi-permeable membrane, and it is driven, or it occurs by the net difference between hydraulic pressure, it's delta P, and the osmotic pressure, delta pi, across the membrane. Yeah. So the general equation for this relationship is, let's say, the G, that the flux should be equal to the multiplication between the membrane's hydraulic permeability times the difference between the hydraulic pressure and osmotic pressure. Yeah. Now, suppose you are plotting your data. So you have the flux here as the y-axis, and then this is the pressure that you apply to the system. Yeah. And then you have some coordinate based on your uh, experiments. Yeah, of course, the larger the data, the better, because then you will have a better line, a better formula which shows your own system. Yeah. So you can see that the effect of osmotic pressure will result in a straight shifted line. Shifted as in not in this 0, 0, but then it's shifted to the right. Okay, so that's the idea when you have like osmotic pressure, meaning that your water is not pure. So when you have the water flux versus delta P, then it will not cross this origin point. Okay, it will be shifted to the right. And this one is actually the delta P. That's the difference in osmotic pressure of your system. So the slope of the line represent the membrane permeability, yeah, because of this. See this one, yeah. And then if you have a steeper line or higher slope, yeah, it means that the membrane has higher permeability. So you're kind of expecting to have like a higher flux per unit of pressure, which is very good actually if you want to have like an effective system, because the amount of water that you have as a permeate is actually larger. Yeah. And then the x-intercept, which is this one here. So this is when the delta P is 0. Yeah? So it's not going to this one. Yeah, it crosses the x-axis, the delta P axis, which is the point of, let's say if it is in, so let's say if this one is the coordinate, then I will write as the x is delta P, and then the y is 0, right? Now the 0 is what? It's the water flux. And then the delta P is what? This is the difference in osmotic, meaning there is actually no movement of water, because the pressure that you apply is actually the same as the osmotic pressure. So at this point, we call that as an osmotic equilibrium. Yeah, the applied pressure perfectly counterbalance the osmotic flow, and it results in a net flux of 0. Now, suppose you have a pure solvent, like a pure water, and when you are asked, what is the osmotic pressure of pure water? Then you should answer confidently that it's 0. Like you don't have any solute there. How would you have the osmotic pressure? So in that case, the osmotic pressure is 0. Yeah. And then if that is the case, then the line will start at the origin, like 0.0. And then if there is any increase in delta P, like you increase the pressure that you apply to the system, then of course you will have a positive forward of flux. Like will have more water. Yeah. And then the solvent will flow into the permeate site. So this is the basis of standard reverse osmosis. What does it mean? It means that you are applying pressure, and it should be like higher than the osmotic pressure. Now, suppose you have solute in your water. So now you have osmotic pressure. Yeah, it's a colligative property. So it's only affected by the number of the solid particle. It is not affected by the type. So whether you have a neutral one or you have a charged one, as long as the number is the same, the osmotic pressure stays the same. Because that's the basic of colligative properties. So now what you have is a feed solution containing solutes that you want to filter off. So you do know that there is osmotic pressure then. Yeah. what is osmotic pressure? So osmotic pressure is actually the pressure needed to prevent osmotic. So if you don't apply a pressure, the osmotic will happen naturally because basically you have a gradient of concentration of water. Because when we say about osmosis process, the movement, the ones that move is actually water. Okay. So if suppose we have osmotic pressure, so the entire line graphs will shift to the right, so to this point, yeah, to the equal amount of C. So this one here is the delta pi, the osmotic pressure. And then suppose you are applying pressure, but then the pressure is less than the osmotic pressure. What does it mean? It means that the flux will be negative. So the solvent will move backward through the membrane towards the high solute side. This is a normal osmosis process. I mean, if you remember, this is the membrane, for example. Let's say you have a solute and this is like the pure water. So of course, if nothing there, the water will go from the higher amount of water, which means low solute concentration, to the one with higher solute concentration because the movement here includes water. That's normal. So if you apply pressure less than osmotic pressure, then the water will move from pure water to the feed solution. Okay, and that's actually not what you want in this case. So this is just a classic osmosis. It's a negative flux. Now the classic osmosis is sometimes we call as a forward osmosis, yeah. But then when you apply delta P, you apply pressure with the same amount of the osmotic pressure, then the flux is exactly zero. Like it's an equilibrium, nothing going on there. There's no movement. What you do there is actually preventing osmosis. Okay, so let's say naturally the water will move from the permeate to the feed solution, but when you apply the pressure equals to the osmotic pressure, then you kind of stopping the osmosis, but the flux is zero. Yeah. Now, what happens if you apply higher pressure? So you increase the pressure. So this one, yeah, based on this graph, then the flux will become positive. When the delta P is higher, the water flux become positive. What does it mean? It means that the solvent will flow into the permeate, which is the one that we want. So in this case, the graph strictly operates in this region, this one, this region, and this process is what we call as reverse osmosis because we actually force the nature not doing osmosis. So we force the water to go from the feed solution to the permeate by applying pressure which is higher than the osmotic pressure. Okay. So the forward osmosis is the normal osmosis. It's driven purely by osmotic pressure due to the presence of solute. Yeah, the different concentration of solute in the two compartments. So it will happen even when we don't apply pressure. But the pressure retarded osmosis, so there is like a hydraulic pressure which is applied, but then the delta P is lower than the osmotic pressure, which is actually resulting in a net positive osmotic flux. And then we have the reverse osmosis, in which the applied pressure completely overcomes the osmotic pressure, reversing the natural osmotic flow to push the pure water out of the solution. Okay, this one, I think this one should be negative, yeah? Okay. Okay, now let's see this one. So suppose you are, you do filtration, you apply pressure, you have the feed solution with a certain concentration of solutes, and you want to have pure water out of it. there might be something that you have to keep in mind. Um, what is it? This is called concentration polarization. So it's scientific term. Let's learn that. So in general, the solution containing solute will have osmotic pressure as a colligative properties. And then the formula is the concentration, molarity times R, the gas constant, and then the temperature in Kelvin. If you are using electrolyte, then you will have the Van Hoff factor. If you have a combination of non-electrolyte and electrolyte, then you have to calculate like the total one. So I'm going to give you an example. Let's say I have 1 molar of glucose, and then I have 1 molar of sodium chloride. So the total C here should be 1 molar glucose plus 1 molar sodium plus 1 molar Cl minus. Cl minus. So you actually have 3 molar. Okay, that's 3 molar of solute, which means if you have another feed containing, let's say, protein with 3 molar, then these two basically have the same osmotic pressure. It just to refresh you about the theory or the basic principle of uh, osmotic pressure. Yeah, because you now understand that there are so many things in the feed solution in the water that you might want to really, not really like cut up in this Van Hoff factor as in electrolyte solution only, but you really have to calculate the total solute there based on individual solute hydrated in the system. Yeah. So the seawater has an average osmotic pressure of 25 to 28 bar. And the brackish water, which has lower salinity, of course, has also lower uh, osmotic pressure. Um, so the brackish water itself support uniquely adapted wildlife like crabs, oysters, and probably certain mangrove trees, which can survive fluctuating salt levels. So it is like having higher salinity compared to freshwater, but still lower than seawater. Now, as I informed you before, that what we have to keep in mind in this membrane filtration process is about the concentration polarization. What does it mean? It refers to the accumulation of solute near the membrane surface. Why we care about that? Because if there are too many accumulated particles on top of the membrane, then you kind of, expecting them, they will hinder the filtration. You will have lower flux. You will have membrane falling. You will have problem with the membrane, and it will reduce the effective difference of the applied pressure, the difference between the applied pressure and the osmotic pressure, and thus resulting in lower flux, lowers rejection, and enhancing the falling risk. And you don't want that. Yeah. And if we want to calculate the modulus of the concentration polarization, this is the formula. Yes, it's an exponential. The Cm is the solid concentration directly at the membrane, and the Cb is the solid concentration in the bulk fluid. So there are actually like two types here. So this one is the permeate. Let's say this is the clean water that you want, and this is the membrane, and this is the feed solution. So we have a barrier here, like a certain distance above the membrane, in which you have here, which is a constant concentrations of the feed solution in bulk. But then you have here an exponential concentration when you move um, shorter or with a shorter distance to the surface of the membrane, you have an increase of concentration, like on top of the membrane. Yeah, that's like that type. But there is also this type. So this one is the opposite. So it is actually like becomes lower. Yeah. So in this case, the mass transfer is limited by the boundary layer. So the concentration of polarization occurs when the concentration of a specific component increases or decreases at the boundary layer close to the membrane surface due to selective transport. I mean, if you are doing membrane filtration, you actually want this selective transport. But probably in some cases, you actually don't know like the exact components of the feed solution. Some might accumulate on top of the surface of the membrane, or some might like really decrease because some of it passed through the membrane. So it could be like two conditions. Um, and then in the case of the pressure-driven processes such as microfiltration, ultrafiltration, nanofiltration, or reverse osmosis, then the solute is typically retained by the membrane. So we don't want the solute in our permeate. Um, this profile can also be found in a process such as membrane-based extraction or membrane-based absorption. That is also in other membrane process where the transport through the membrane takes place by diffusion rather than the convection. Yeah, in which the concentration profile will be similar to this one over here. Yeah, since in this case because it is like more affected by the diffusion, then the component will permeate faster through the membrane, being in the boundary layer where the transfer is limited by the diffusion of the solid. Probably because of difference in concentration, for example. And then this profile, the B here, yeah, uh, might be present in gas separation, evaporation, dialysis, electrodialysis, or membrane crystallization or membrane distillation. Yeah, we will discuss that later. And then the concentration polarization that we discuss here will produce a decline in the transmembrane flux. So this is for this one, yeah, the top picture. And then this might be very severe, such as in microfiltration or ultrafiltration, or it can also be negligible if we are having gas as the particle that we want to separate. And then regarding the retention, the rejection percentage, it also may lead to a lower retention if low molecular weight solutes such as salt are considered, or it may lead to a higher retention, which is the case of mixtures of higher molecular weight solutes. And then the concentration profile. So this is the profile that for example, this is the normal one. So this is the profile from the bulk fluid. From this is constant. So the membrane surface. So this is near the membrane surface. Then it will, in the form of the exponential increase, yeah, as the concentration polarization. And then this one here is the permeate concentration, and then this accumulation, the increase of the concentration of the permeate on the surface of the membrane will create a boundary layer. So you kind of, having an additional layer on top of the membrane, okay? And then in this layer, the concentration of the solute is actually significantly higher compared to the one in bulk. So now you imagine, so you have a membrane, the working membrane that you use, you have the bulk, and you have a certain layer on top of the membrane, which has a higher amount of solute there. Yeah. So the bulk fluid, the CV, yeah, it's the main body of the fluid, the bulk, and and it's normally the lower concentration of the solute. And then we have the one in the layer here, yeah, or here. This is the boundary layer. This is a region of fluid adjacent to the membrane surface where the fluid movement is restricted. And then in this case, the convection carries solids toward the surface while they are simultaneously rejected by the membrane. So you have an accumulation of concentration. And we also have the membrane surface, the CM, the concentration peaks there, like that should be the highest concentration present in the system. And this happens because the rate at which the solutes are brought to the membrane by the convective flows exceeds the rate at which they can diffuse back into the bulk. So they can go here, but then probably, with a higher rate, but then when they want to go back to the bulk, the rate becomes slower. So you might imagine that, for example, in this case, we have an increased concentration. Yeah. So now I hope you understand what is going on in the membrane when you are using it. So you do know that there is a concentration polarization, then there might be an accumulation of solute on top of the membrane surface that might hinder further filtration. Yeah. And then the key dynamics of the profile is that, so you have the convection, like when you shake it, yeah, and you have also diffusion. So I'm going to draw a schematic. For example, you have a cell. Suppose you are using a round membrane, something like this. So this is the feed. So let's say this is the permeate. And then you have a convection over here, which can move around, move around. So you can imagine that you have a convection, which might be the driving force of the movement of the water from the feed to the permeate. But then you also have a diffusion, right? Diffusion probably is there because of the difference in concentration. So in this case, the profile will reach a steady state when the convection transport of the rejected solute toward the membrane exactly balance the Brownian or diffusive back transport of the solute away from the membrane into the bulk. Yeah, so that is the convection versus diffusion. And then there is also osmotic back pressure. So a highly concentrated layer at the membrane surface, this one here, creates an osmotic pressure, right? Why? I mean, you have a solute there with a higher concentration. So if you calculate the osmotic pressure, then you can expect to have a higher osmotic pressure because the number there is larger. Yeah. So now this osmotic pressure will then oppose the driving force to the filtration process. And what does it affect? Then it will reduce the permeating flux. So now you see, now you can even explain when the flux becomes slower after a certain time of using a membrane. You do know that the flux is slower, but then as a scientist, you have to explain why. So I hope in learning this, and I mean during your summer course over here, you really expand your logic of thinking, trying to explain whatever phenomena that you observe during, let's say, experiment in the lab, and then you try to explain that based on the knowledge that you know. Yeah. So in hope that you can explain better whatever results that you get from your experiments. Okay. So in this case, you kind of, explain that, oh, I have a lower flux after several days of using the same membrane because I know that on top of the membrane there is, a concentration polarization, and then it has osmotic pressure higher, then probably the applied pressure, then this osmotic pressure work oppose these applied pressure. That's why then the flux becomes lower. See, it's kind of cool if you think about it that you can explain such phenomena around you. And then there is also fouling and scaling. So imagine that you have a membrane and then you have like a very high concentration on top of it and it exceeds the solubility limit of the solute, then it can lead to even precipitation. I mean, you have to keep in mind that when we have a solute, meaning that it is hydrated by the water, but then if the amount is too much, if the amount is very high in a certain area, let's say in this case it's on top of the membrane, then they might coagulate, they might precipitate, and that will hinder the filtration. It may be forming precipitation, scaling, or even gel layer formation, and they will severely degrading the membrane performance, and you don't want that. Yeah. So in that case, there is like, or there should be an operational control. So the thickness of this profile, this one here, yeah, and the severity of the concentration polarization can be minimized by what? By increasing the cross flow velocity. As I described before in the beginning of the presentation, that you have the dead end or the cross flow velocity. Now the cross flow velocity kind of helping having this one. So you also have to think that in science, when you face the problem, you should focus on finding the solution. You are not focusing on thinking about the problem. I mean, even if you don't think about the problem is there already. So you should really focus on finding the solution, not really thinking about the problem, but thinking about the solution. So if you, for example, you have a system, you have a membrane, you have a permeate, but then suddenly it stops or suddenly the flux becomes smaller, you're kind of thinking, oh, what should I do to prevent this? What is the solution of this? You don't like spend your time arguing what is going on or whatever, but you think about, okay, what can we do? Yeah. And you also don't take it personally, like you don't think your experiments go bad because of you doing it. It's not that kind of thinking, but you just focus on, okay, what can I do to solve this problem? What should I read? Who should I ask? Like focusing on finding the solution, because whatever that you do, whatever that you observe in the laboratory, it's just part of the experiment. It's just part of finding whatever nature hold. And that's why it's called research, like searching back, yeah, and trying to understand what is going on. So you can use the cross flow velocity, and then it will optimize the channel spacer to create turbulence, and also keeping the transmembrane pressure within the optimal operating range. Yeah. Yeah. So next is the membrane performance parameters. So if you are having a system, in this case, membrane filtration, you might want to have a standard. Like you might want to know, in what case do I say it is a good thing, like up to the standard, or it's not up to the standard? Like you should really like define the parameter. So for this membrane performance, we have what we call as permeability, and then rejection, and also selectivity. In general, you want to have a high permeability, a high rejection, and a high selectivity. That's kind of the golden standard. But of course, there's a trade-off. I mean, you might also notice that in nature, we should try to accept the nature as the way it is. There might be a trade-off between permeability versus selectivity. So sometimes you have a higher permeability, but it's not selective. Yeah, most of the particles go or pass through the membrane, in which probably we don't want that, because then the water becomes still dirty. because they're having like this low molecular solute or probably concentration, some concentrations of the salts. Yeah. Um, so the ideal one is that you want to have high flux for peak rejection, and you also want to have a membrane which is resistant to falling because you don't want to have a decrease in flux over time. And you also want to have a membrane which is chemically and mechanically robust. So whatever there in the feed will not break down the membrane. And then mechanically, because you are applying, for example, high pressure to it, but still the membrane can stand it. So it has good mechanical properties. And you also want it to have in a low cost that everybody can buy it. Not really expensive, because if it's too expensive, then people might look for other alternative, which is the cheapest or cheaper way. Yeah. So now let's talk about the permeability and selectivity trade-off. Yeah. So this is actually the same picture of a membrane, which is very nice that you can see the cross section of it using SAM. Now the permeability selectivity trade-off is a fundamental limitation in desalination membrane technology. It's like it's a fact. It is something that you have to live with it. You might think of something to, but it's just right now that is the problem. That is the limitation of this technology. So what is the limit, or what is the trade-off? So when you increase the membrane's water permeability, the speed at which water flows through it, high flux, it will enhance its selectivity, its ability, the membrane ability to block dissolved salts. Yeah. So in normal way, for example, you are start working with a membrane, and then you find that your system, has high flux, but no rejection. That is actually normal. But of course, if you are doing research, then your job should be able to increase it somehow. Yeah. Now, the underlying mechanics in this, we have a solution diffusion model, as in the desalination membranes, like thin film polyamide, function by dissolving water molecules and pushing them through the polymer network. So, the polyamide, for example, has CONH, the carbonyl and NH, so they can interact with water via a hydrogen bonding, for example. So the water can pass through. But then the water salt selectivity relies on differing solubility and diffusivity rates. So if you have like a hydrophilic membrane, for example, you will have a high flux because the water can pass through easily. But you also have a higher permeability to salt because the salts contain ions, and then they can also interact with the. In that case, you decrease the selectivity. Yeah. And there is also the upper bound. So in a log plot comparing water permeability versus water salt selectivity, the membrane performance forms a diagonal line known as an upper bound. In this case, the membrane pushed to the right have higher permeability but poor salt rejection. And then moving to the upper left corners means high salt rejection but slower flow rates. Something like this. Yeah. So, for example, we have water and salt perm selectivity, and also water fermions here in liter per meter square per hour. And then we have this diagonal as overcoming the film selectivity trade-off. And this is for the osmosis membrane. It contains polyamide on top, this one, and it contains polysulfone in the bottom of it. And then, for example, it is the water having a DMSO to activate the reverse osmosis membrane. So the focus here is we want to break the barrier because we want to have a high selectivity and also a high rejection. So we kind of wanting, okay, I want to have both. I want to have high selectivity and also high um, rejection for the membrane, which is the ideal parameter for the membrane. Um, so in this case, the researchers actively seek to overcome this trade-off. So you might see that for the ones who are interested in doing this research, for example, because they care about the environment, they want to provide clean water for human, or simply because they want to do business, they want to sell, a good membrane, that's also fine. Whatever to work on it. So many are doing this research in membrane, yeah, to overcome this trade-off to minimize the energy cost in the, let's say, seawater purification or package reverse osmosis process. And then this approach might include, for example, solvent activation, like doing, immersing in DMSO and water. So what is the purpose? So one is altering the structure of the polyamide layer with chemical structure. So for example, here using the MSO and water, what does it do? It wants to enhance the water permeance while retaining sodium chloride rejection. So now you might think, or even if you read something. So for example, here you heard an information that scientists using a mixture of DMSO and water to activate the membrane. Actually, when you see this information, you should think like, how do they come up with that idea? Why do they try it? How? Why? And so on. Yeah. It should encourage you to think why other scientists do that. What is the reason? Now, sometimes the reason they found that the immersion in DMSO and water might not be, it could be accident in the laboratory. Not necessarily like, I'm thinking I'm going to use DMSO. Not necessarily that one. Sometimes it's an accident. For example, there's your friend working with DMSO and water inside you, and you kind of, immersing your membrane. That can happen. But of course, there's also like people who is lucky with the experiment and then they kind of, I want to try this. No reason. I just want to try it. And okay, let's just try with whatever solvent in the laboratory. So in this case, you should be in a rich laboratory in such a way that it allows you to play around with whatever available chemicals in the laboratory. Because I mean, in the experiment, it's something trial and error, and it needs chemical, it needs funding, to be able to think because to do something. Because sometimes you have the idea, but there's no fun in the laboratory. I mean, then you cannot realize your idea. But anyway, the second approach could be using nanomaterials, like you kind of thinking okay, I want to increase the selectivity. So somehow I want to hinder the flux. Yeah, I want to make it more selective. So okay, let's make the pore smaller. So what should I use? I'm thinking about nanomaterials. And then you kind of okay, let's just choose whatever available in the lab or whatever nanomaterial that you can buy or you can try. In this case, people using artificial water channel or carbon dots or metal organic framework to provide highly uniform sub-nanometer pathways that facilitate water flow while blocking the ions. If you are thinking, how do people come in with this idea? Well, first we have to think that they have interest in doing this research, but sometimes it's just the way your thinking work when you are working with something for a long time, like for a very long time. Like you're working with it, you think about it every day. You make a schematic picture because you want to understand whatever is going on with your research. Then in your mind, like human brain is very interesting. Your mind will also kind of, thinking those problem and having a link of it. And even if you saw something like a network, like people present you about the network, about the research, even the research is not connected to yours. But when you're saying, let's say they present you network, in your mind you can think, that looks like pores in the membrane. Maybe I can use that. Maybe I can combine that. Okay, so that's kind of um, intuition when you're working with something for a long time, or if you are reading knowledge regarding something for a long time, you might develop intuition. You might develop, like, okay, I can do this, I can do that, or I cannot do that, it's not possible, or it's possible but it's expensive. Those kind of information that you get, that is after you are having a lot of information in your brain. So you are, as a student, for example, you are encouraged to read more knowledge, read more books, or attend several seminars, for example, to enhance your information. um, so the next one here is the membrane configurations and models. Yeah. So the common geometries is a flat sheet, could be plate and frame or spiral wound, and also sometimes it is formed in the tubular or hollow fiber like cell side or bore side fit. There is also like spiral wound, like leaf wraps around the permeate tube. There's also like feed spacers. It has high packing density, and it is actually the industry standard for reverse osmosis or nanofiltration. There's also in the form of hollow fiber, which is self-supporting, very high packing density, and it is mainly used for microfiltration or ultrafiltration, and some in reverse osmosis. So this is the example. Um, this is the internal structure comparison between spiral wound and hollow fiber over here. Yeah. So you can see that there is like a central tube over here, and there are like several layers over here. There's also like feed spacer, the membrane sheet wrap, and so on. Yeah, so you can see this one here. And there is also something like this. So you have these like small tubes over here, a very like a lot of small tubes, yeah, in the form of hollow fiber. And then you kind of packing them together, making a fiber bundle, and then you wrap it using a shell over here. So it could be this possibility, or you can also, for example, combine them together. Because yeah, sometimes when you are working with something, and you have to expand your ideas of research, you have like a certain options, and probably like one of the option is mixing several options. That's also possible there, as long as you are supported by good facility, good funding. It's okay to explore around. um and there is also this spiral membrane configuration. Yeah. uh So this is the feed solution coming to this one, and this one here we have like a several layers of membrane over there, and then the permeate over here. Yeah, so the permeate will go to this one here. So we have the like a hollow fiber in the middle, in which they will contain the permeate, like the clean water that we want. And then the outer of these is the several layers of the membrane in which they will work at as the filtration going on. So what should you consider when you are designing the module of this filtration? So in the packing density, which is plate and frame, then it should be around 100 to 400, and then for the spiral one, it should be 800 to 1000, while the hollow fiber can up to 10,000. So it's quite a lot. Of course, in this case, if it is in the experimental stage, then you also like play around with the number yourself, according to what is available, what can you produce. That would be the limit of your work, according to what is available. And then for the flow channel height, the special design like mid-light to promote turbulence and reduce falling, yeah, or the concentration polarization. And then there should be also the pressure drop, which will ease the cleaning, and you should also consider the replacement cost after several times of using. And then the operation mode, it could be a dead end filtration, like the feed perpendicular to the membrane, yeah, and it probably promotes cake builds, like falling on top of the membrane, but it still can be used for small scale microfiltration and ultrafiltration. So even though it has disadvantages, it is still used because it's actually cheap. Yeah. And also there is like a cross flow filtration in which the feed is going in a parallel flow regarding to the membrane. So the sweeping of the flow will limit the formation of the cake, of the falling on the surface of the membrane, and then it is actually industry standard for the continuous process. It is expensive, it's more expensive, but in the long term, it is actually more economical. So you can see that expensive or cheap depends on the source that you have, whether you can afford, buying something cheap for a short term or invest in higher cost, but it can last a longer time. And then it can also multi-stage RIs, which concentrate staging for high recovery. So it's made of like multiple systems. Now, for the membrane flow scheme, so the membrane flow dictates how the feed, permeate, and the concentrate streams, yeah, are routed. Why? So the purpose is to optimize the separation efficiency and also energy consumption. You don't want them to, let's say you want to have a certain permeate and you want to have it in a shorter time possible. And also the product purity, the standard of the drinking water that you want, for example. And then the three primary configuration include single stage, multi-stage with recycle, and there is also concentrate recirculation. And they offer distinct advantages depending on your target recovery and also solute concentration goals. Now let's see. So the first one is a one-stage reverse osmosis system. This is just an example. So you basically have a feed water. This water includes whatever pollutant there in the water, and then you want to have a permeate water that you want, and there might be concentrate water after the feed water moves to the permeate water, and then you are using one reverse osmosis membrane. So it's one stage, quite straightforward. Yeah? So in this process, the feed passes through the membrane elements exactly once. That's why it is called single stage. And then the permeate, the purified product, is collected, and then the concentrate, the retained solute, is discharged. Now, if you're using the single stage system, then the recovery rate is low to moderate and typically limited to 15% or 50% per pass, depending on the feed type. And then it is as used, for example, system with low recovery requirements, simple operation, or heavily falling prone fluids. And then the second one is the two-stage RO system. It's an example of the multi-stage. So in this case, the process is that the concentrate, yeah, the concentrate from the first group of membrane module serve as the feed. So you have like another step, yeah. So for example, you have the feed water. It goes to the membrane, right? And then you have a concentrate. Now this concentrate going back to this one over here. So the cascade continues through successive stage to maximize product extraction. So you don't draw away the concentrate. You flow them through a different membrane. So it means that you have several steps of filtration. And a portion of the final stage concentrate is often recycled back to the beginning of the system. So it's like circular system. That is actually good. I mean the problem is just cost. It might be cost more, but it's actually like a good thing, especially if you think about the efficiency. The circular process is better. And then the recovery rate is very high, so often 75% to more than 90%, because it minimizes waste of the water, of the concentrated water, by progressively squeezing more product out of increasingly concentrated streams. So it is very important, especially in the area with a high level of drought. So let's say the amount of water is not too much, then of course you don't want to waste water there. So even if it is like first it's like a dirty water, and then you kind of um, filtrate them one step, more step, and more step, and more step. You want to have like all the water. Then in that case, you are going to have, or you are going to apply the multi-stage system. Yeah. So it is best used industrial separations where high yield is critical. For example, reverse osmosis desalination or probably gas separation or dairy processing. And then there is also a concentrate recirculation. Yeah. So in this case, so a portion of the concentrate stream is continually returned to the suction side of the primary feed pump and then blend with the fresh feed. So you kind of mixing them together. And the recovery rate is high, which allows for compact, small scale unit footprints. But then there is a trade off that is the energy costs are relatively high because the feed pump must continuously handle a higher total flow rate because it has like an additional flow from the concentrate water. And then there is also like a blending feed between the fresh feed and the concentrated feed, yeah, in which the concentrate will increase the average feed salinity. So it actually like add more work. Thus, it requires higher feed pressure and resulting in slightly saltier permeate. It's probably, I mean, if it is about the 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 amount of the salt in the permeate, that also will depend on what kind of membrane that you are using. But the total work you are using in the pump, that becomes higher, which means you should invest in a better pump, and it probably costs more electricity, for example. So this is an example using recirculation of the reverse osmosis concentrate. Yeah. So for example, you have wastewater over here, you have a permeate, and there's a tank over here, but then we have also a feed here. There's a membrane, there's another permeate, and it's like a loop over here. And then it goes here to the tank, and it is recycled back to here. So it's kind of looping. Yeah. So it is best used for small-scale commercial RO systems that require high recovery rates in a limited space without building an expensive multi-stage plant. There is also a consideration. Yeah? If you are, I mean, if you are thinking about providing good water facility for a city, for example, you are talking about thousand or maybe hundred thousands of people. So the amount of water is quite large. It means that you really have to have a very good facility, and it requires a very large area. And if you want to work using, let's say, not so good water, then you need like a multi-stage facilities. And might maybe in some area that's not possible to the limitation, then these concentrate recirculation might be the option. Okay, now we're going to move to the key membrane processes for water purification. Yeah. So for the microfiltration, so this is the same picture of the polypropylene microfiltration membrane, um, uh, which is used in the Orange County Water District. Yeah. You can see that, I mean, this is the scale. This is around 200 micrometer. So maybe the diameter is also around 300 micrometer. So the pore size is around 0.1 to 5 micrometer here, around here. And it can remove the bacteria, protozoa, and also some turbidity due to the total dissolved substance in the water. And then the operating pressure is around 0.1 to 2 bars. And then it is often used as a pre-treatment for reverse osmosis in such a way that, for example, you want to have like not heavy reverse osmosis process, then you do a pre-treatment using microfiltration. So you kind of coupling different type of filtration in the system. And then it can be submerged. Yeah, it's in membrane bioreactors, or it can also be pressure driven in case. And then the next is the ultra filtration. Yeah, so it works around 2 to 100 nanometer with a molecular weight cut of 1 to 500 kilodalton. Yeah, 1 to 500 gram per 500,000 gram per mole. It can remove viruses, colloids, and even macromolecules. And then it is normally used for drinking water production, direct portable, and then replacing conventional sand filtration plus disinfection. It is actually an excellent pathogen barrier. In this case, the log removal is more than 4 viruses. And then the standard target for the uh, log removal value, yeah, by organism type. So in water treatment, medical sterilization and food safety, the regulatory bodies like the EPA, they have like a specific target of LRV, yeah, because different organisms have varying resistance levels. Now the LRV itself is calculated like this, and then when we say it is log 1, it means that 90% uh, retention. Yeah. So you kind of expect that 100,000 pathogens still remain in the system. But that if you have, for example, log 5, log 4, then you have 99.99% retention. So let's say only 100 pathogen remain. And then if you have higher log, like log 6, then let's say only one pathogen remain. Of course, if you want to have like a healthy water, you don't want to consume some pathogens in water, then you might want to have or to aim for a higher log. But then um, the institution has a standard which still deem quite safe for human for water and for drinking water. So, for example, for the bacteria like E. coli or Salmonella, the standard is log 4 to log 6, so around this value and this value, yeah. And then the bacteria itself is highly susceptible to chemical disinfectants and heat. While for the viruses such as norovirus or rotavirus, the aim is at least log 4. So log 4 is around this, like remaining 100 pathogen inside the drinking water. And these actually require a strong oxidation or UV exposure, yeah, to disrupt their protein capsids. And then for the protozoan, yeah, such as Giardia or Cryptos, Poridium, the aim is reduction of log 3. So log 3 is around this one, like 1000 remains, yeah. And then in this case, their thick protective outer walls make them highly resistant to standard chlorine. They often require UV light or physical filtration. Uh, wait. And then there's also bacterial endospores like Clostridium difficile, which aim for at least log 6. So you only want to have like one pathogen remain. Because in this case, the spores are the most resilient life forms, and you don't want to consume them, and it serves as the benchmark for the medical grade sterilization. Yeah. Um, and the next one is the membrane bioreactors or MBR. So it combines activated sludge biological treatment with microfiltration or ultrafiltration membrane separation with submerged or side stream. And usually it is used with biomass concentration with around 8 to 15 gram per liter, yeah, with small footprint, excellent effluent quality, and so on. And then the permeate will go directly suitable for the reverse osmosis feed or reuse. So something like this. Yeah. This is for the activated sludge treatment process. So here we have the wastewater, and then we have a stage of solids removal, filtration, and there is a pre-treatment over here. There's also aeration zone, and there's a settler, for example, sun filtration, disinfection, and we have like a drinking water. But then, if we compare it to the membrane bioreactor process, the beginning is the same. Like, okay, I have wastewater over here, remove the solid, we have pre-treatment, aeration, but then this one over here, it is replaced by the membrane system. So you have the membrane over here, you have the sludge, but you have a permeate effluent, and it's probably still requires some disinfection. I mean, it really depends on what kind of pathogen inside, which might require still disinfection. Then you have uh, water that you want. Yeah. Now, for the nanofiltration itself, if it is, or sometimes it is called as a loose reverse osmosis, and then the pore is around the pore size is around 0.5 to 2 nanometer, and then the molecular weight cutoff is around 200 to 1000 Dalton. So the idea when I mean, why do I want to use nanofiltration? Because the size is very small. So this comes to the case when you want to remove multivalent ions like calcium 2 plus, magnesium 2 plus, and sulfate ions. So for example, probably you have water in your home, but then its hardness is quite high, containing calcium 2 plus or magnesium 2 plus, and you want to remove it, then you might want to use nanofiltration. Or if there is a natural organic matter, or if there is like coloring in your water. So suppose your water should be colorless, but then it's like quite yellow because maybe ions are there. You want to remove them, or probably there's like pesticides. Maybe your home is close to, I don't know, agricultural field that maybe some fertilizers accumulates over time, and there's like a high amount of ammonia in the water drinking, then you want to remove them. Or maybe some monovalent can even be removed by using nanofiltration, just some of them with size big enough uh, in regard to the pore size of the nanofiltration. So now you have the idea when to choose which type of filtration that you are going to use based on the pore size. So what is it applied? So for example, this is for water softening, meaning that it reduces the amount of calcium 2 plus, magnesium 2 plus, and also color removal, and also desalination of specific streams. So it really depends on like what is the water source, what is the content in the water source for the feed solution. And then the dominant mechanism in nanofiltration is size exclusion, because I mean, the pore size is very small, so anything larger than that should be retained, not passing through the membrane. There might be also charge effects, yeah. The surface that's critical, probably negative at neutral pH for polyamide. And the trends here is, for example, we have valence effect, like the higher charged ions experience stronger electrostatic repulsion from the membrane surface. And we also have the size effect, which is ions with larger hydrated radii are physically blocked by the membrane pores. Or for the monovalent ions, it shows lower rejection due to the weaker electrostatic interaction and smaller sizes, while the multivalent ions it can achieve high rejection rates, often exceeding 95% due to the strong starch repulsion. So in this case, when you are talking about nanofiltration and you want to remove ions, in your mind you should think about, okay, first I have like smaller size, like a very very small size. So in theory, the size which is larger than that should not pass through this membrane. But then when you deal with ions, then you should also think about the electrostatic uh, interaction. So what you need is actually you want your membrane to do repulsion of the ions so they don't pass through the membrane. So it's like uh, still in the feed solution. Yeah. Which means that you might need to modify the chemical structure of the membrane that you are using, uh, such as, for example, oh, I'm going to use polyamide or I'm going to use other type of the membrane. And you can think, like, do you have ions on the surface of the membrane, or should you introduce it? Should you modify it covalently and so on? It's basically like chemistry. Yeah. And then if you see this one, uh, this is the percent rejection, and this is the feed pressure. You can see that the top here, this is for the sulfate ion, so it's a bigger ion. You can see that the percent of rejection is quite high, meaning that the membrane rejects sulfate ion, which is good if you don't want to have sulfate ion in your drinking water. And then the next here, this one here, the calcium 2 plus, yeah, this one. And then we also have these bicarbonate ion, and then this one here is Cl minus, and this one here is this one I think is sodium plus. So you can see that the ions with larger size, with larger valence, normally it is more retained, rejected by the membrane. But then a smaller ion with smaller valence, it might be tricky. Like for example, this one here, and the pressure is very small, so 50% is rejected for plus, which means that your drinking water still contains 50% of sodium plus compared to the feed solution. You still have like so many Na plus ion in the drinking water. And if you don't want that, or I mean, you should also then compare it to the standard of the drinking water. But then if you don't want that, means that you have to use higher pressure. So for example, you increase from this to this one. Yeah. I also want to point out the way you expand the idea when you are doing research concerning a brain. So, for example, you are researching a membrane and then you want to deal with ions, and you kind of thinking, oh, I want to remove these ions. So you kind of thinking, okay, what ions do I have? If you're working in a laboratory, you actually like making a fit solution with similar to the one that you want to have. Not necessarily, directly applying a wastewater, but you kind of making water and then you add, ions to it. Because then you have a controlled experiment. Because the idea when you study in the laboratory is you want to study it as a singular observation. You don't want any other aspect influencing your data. So let's say you work with pure water and then you add sulfate ion into it and then you see what is going on, and then you have this data over here, which is very nice. Then from this data that you know that your data is good, with a good repeatability, then you are sure yourself that whatever conclusion that you derive from your data is good. I mean, you can defend it. It's responsible data. And that's what you have to keep in mind really when you are doing experiment in the laboratory. So with the knowledge that you have, you make sure that whatever data that you are doing is valid as a scientific experiment, that you are responsible for it. Your data is good with the scientific approach, and whatever conclusion that you have, you can be confidently responsible for it. So when you, let's say, publish it, so the public can read your paper and they can have a new knowledge for them, and they might also expand your research. And actually, like, a good thing to do, that you expand your knowledge. uh, you are doing something to add more information to the currently present data in the literature. And then other people might learn something from your data, which is actually nice, I think. Yeah, you contribute to science. Many generations later, we learn from you, learning from those small experiments that you do in the laboratory. I think that is very nice. Next is reverse osmosis. Yeah, so this is a dense membrane because the pore size is very small. It rejects more than 99% of all dissolved salts. And it is only a primary technology for seawater and brackish water for desalination. And or for example, you want to have ultra pure water production. And then it is using, for example, TFC, polyamide membrane. It's a thin film composite polyamide membrane with salt rejection more than 99.7%, which is very nice. And then operating pressure is quite high. It's 55 to 70 bar for the seawater because it has higher salinity. But if it is a brackish water, it's required pressure is lower to 10 to 25. So you can imagine that the membrane that you are using for the reverse osmosis should be the membrane with a very high mechanic properties. So you can also think that as a chemist, it was like, I want to offer solution for this drinking water problem. Like, I want to make sure like people in the area has like a good drinking water. And you might be, for example, interested to do this research in membrane, or probably you even want to have a company dealing with this membrane, and maybe you are doing research and so on. Um, but you can see that the idea is that you are using your knowledge, in this case, chemistry, in the membrane science. You use your knowledge to solve the problem in the community. So you kind of, giving back to the community. It can be pure research as in an academic or in government institutional facility, or it can be in economic business, like I want to sell it. I want to sell my invention, which is fine. I mean, it's actually fine if you find something, if you find a new technology which solves the problem in the community, and you are rewarded for it. You are becoming richer because you sell the membrane, which is beneficial for people. But you're getting rich. That's fine too. I mean, you should be rewarded for whatever you invent because it takes a lot of work. It takes a lot of investment. I think it's normal if someone gets rewarded for it. But the idea is the same, that you are contributing to the community by using your knowledge. I think that's a very nice idea. In this case, for example, we have the knowledge of the reverse osmosis. By using, for example, we have the wastewater over here going to this one. Yeah, this is some layers of a membrane. And then you have the permeate, the product that you want coming from this. And then the layers of the membrane itself, it could be membrane, could be feed water carrier, another membrane, permeate carrier, another membrane, and so on. Yeah. So you kind of wrapping them together. So when you imagine that people come to think of this, and then they produce this product, and then it is has a good function, beneficial to the humanity, to the environment. I think that's very nice. Like, you are applying your knowledge like you are being useful to other human beings. And then next here is the process design, as in energy consideration. So in a reverse osmosis system, specific energy consumption measures the energy used to produce a cubic meter of permeate. And then the total energy consumption, the specific energy consumption, is highly dependent on the system component and the use of the energy recovery devices, which significantly lower net operational energy requirement. Now, the specific energy consumption here is around this, yeah. It includes pretreatment and distribution, while the energy recovery device, so the pressure exchange and recover 95% energy from the brine. There's also thermodynamic minimum energy for the seawater, which minimum 50% recovery, and this is also the energy as a practical limitation. And if we compare it, so the system section include pre-treatment, and the component involved is, for example, media filters, cartridge filters, and so on. And it contributes to energy consumption around 5 to 10%. And then you might also use high pressure pump as in membrane. It might maybe the highest consumption there, around 65 to 80%. And then you have the membrane system, the reverse osmosis. It might consume 10 to 15%. And then you also have these energy recovery devices, which recovers hydraulic energy from the high pressure brine. It might step up to, let's say, 40 to 60% of total energy. And you also have the post treatment, such as remineralization, because you don't want to drink pure water. It's not beneficial for your body. You actually need ions in it. And probably pH adjustment, because let's say the acceptable drinking water should be around 6.5 to 8.5 pH. And then you also need to distribute the water, so that probably add cost, which let's say it's around less than 5% of the total cost. So this is an example of the energy consideration in the river osmosis design. Of course, it can be different if you really like apply it in real case scenario. Depends on how large and so on. Yeah. And then for the concept, we have the forward osmosis here. Yeah. So the natural osmosis is that water flows from low salinity feed to high salinity draw solution across a semi-permeable membrane. That's like a normal osmotic, because we have water with a very high number of water, and then it will flow to the compartment with higher solute concentration, because there the number of water is like less. So you get this movement of water across a semi-permeable membrane. That's the normal natural osmosis. And then in this case, you don't need hydraulic pressure, except if there is like minor flow resistance, or if there is like a falling, which produce a backwards osmotic pressure. To lower, so you want to apply hydraulic pressure, for example, to lower falling tendency and for reversible falling. And then the challenge is that the draw solution regeneration to recover fresh water and concentrate solute. Yeah. And these still use, for example, brine concentration, produce water treatment, or emergency hydration bags. But then in this case, the forward osmosis is a process in which the water molecules from saline water moves through the semi-permeable membrane toward the draw solution, which is maintained at higher concentration than the feed solution. So in this case, the forward osmosis mainly use osmotic pressure gradient and not the hydraulic pressure gradient. Yeah. So, for example, this is the saline water tank. Then you have a semi-permeable membrane. You have a freshwater plus draw solution, and you have the draw solution recovery unit. You also have, probably if in your water you have like ammonia or CO2, and then you go back to this one because you want to make sure that only water comes, and then you have like a fresh water. And then from these, you can have the brine water, water with a very high salinity. Yeah. And then for the forward osmosis and pressure retarded osmosis here, you can have for example, for wastewater or desalination hybrids, that the forward osmosis, yeah. But then the pressure retarded osmosis use osmotic energy to generate power, like using the salinity gradient power. And then in a forward osmosis system, the draw solution becomes diluted as it extracts water from the feed solution. And then to maintain the continuous operation, the draw solution should be regenerated through pure water recovery. And it could be achieved using either thermal regeneration, using heat, like you heat the system. And then, or you are using the pressure driven membrane such as nanofiltration. So this is a schematic diagram of the lab scale forward osmosis system for the A, and then the B here is the recovery of diluted draw solution through nanofiltration system. So in the beginning, you have a feed solution, you have a pump here, you have a membrane cell, you have a diluted draw solution, and then you also have a pump over here, and this is the draw solution also, and this is the water bath. And then the diluted draw solution here, you have another pump, and then you use the nanofiltration membrane. You will have a permeate, and you will have a concentrate, which is becomes the draw solution. Yeah. Now for the draw solution recovery, so in this case, we can have the thermal draw solution recovery, meaning that it is typically used when you have a volatile draw solute like salt or ammonia or carbon dioxide. And then the process is that you have a diluted draw solution, you have a heat exchanger, and you have a distillation column or stripper. So you heat the system, yeah, using heat or solar energy, and then you will break the volatile solute. Like maybe there's a decomposition of the solute becoming volatile gas such as ammonia and CO2, and then pure water. And you expect that the gas should be, removed from the solution, yeah. So the gas solute routed to an absorber, so the absorber will absorb gas, and where they are redissolved into the recovered pure water or recreating the concentrated draw solution. There is also the second one, which is nano filtration draw solution recovery schematic, and it is using multivalent draw solutes such as magnesium chloride or organic salt or specifically engineered polyelectrolytes that cannot easily pass through the nanofiltration membrane pores. So in the process is that you have a diluted draw solution. So the draw solution includes everything in water, and then you have a high pressure pump, and then you forward this solution into the nanofiltration membrane module. In this case, the mechanism is that you have a hydraulic pressure applied and forcing water through the nano filtration membrane, and then you hope to produce pure desalinated water as the permeate. Yeah, and then in this case, the concentration is that the bulk of the draw solute is rejected by the NF membrane because the NF membrane has like a very small pore size, and then it will remains in the retentate, yeah, the one rejected by the membrane, and this concentrated retentate stream is then recirculated back to the forward osmosis loop as the regenerated draw solution. So in this case, you don't want to waste the water, so you make the retented, the concentrated retented go back to the draw solution. And then the next we have also a membrane distillation here, yeah. So it's a thermal driven process using a microporous hydrophobic membrane. In this case, the water vapor transport across due to vapor pressure gradient in which the liquid water will be repelled. And then here we have a high rejection of non-volatiles and can handle high salinity brines, and it utilizes waste heat. And the configuration could be DC, that is direct contact. It can also be air gap, and it can be also a vacuum. Yeah. So it's just a matter of applying something close to the membrane in such a way that you create a gap. Yeah. And then you can, make the the particles that you want to reject to be rejected. In this case, we have here, yeah, for the direct contact membrane distillation, the temperature profile shows a continuous stepwise. So this one over here, yeah, across the module, and then the temperature drops steeply through the hot thermal boundary layer over here, yeah, and then exhibit nearly linear decrease. This one over here. Across the hydrophobic membrane, and then drops again through the cold thermal boundary layer. So you basically have two sides. So one is hot, one is cold. You kind of evaporating the water, and then this evaporated water will then be liquefied to become a liquid. So then, the gas, let's say the gas water pass through the membrane, but then when you have like a colder temperature, then it will form liquid. That's the idea. Yeah. Yeah, so the temperature profile illustrates the transverse temperature drops across the liquid, highlighting the phenomenon of temperature polarization. There's also electrodialysis here. In this case, for example, using ion exchange membranes under electrical potential difference, like cation exchange or anion exchange membrane. Yeah. And then it can remove ionic species, not for non-charged organics or pathogens, so it's specifically for ions. For example, here we have polymer matrix, and then, for example, because it is negative, then the Cl is rejected, but then the K plus can pass through it, for example. And then also, probably if there's a monovalent selective cation exchange membrane, it can also be modified. Yeah, so there's like a positive here, like a thin layer, and then so only the lithium plus over here with single valence can pass through, but then the cation here, the magnesium 2 plus, cannot pass through the membrane if it is making a selective membrane. So the application is for the brackish water desalination or nitrate removal or the food or dairy. The idea is that here there's also like electrodialysis reversal, which reverse polarity to control scaling. And then the next one here is there's like a merging hybrid process. So in the end, people want to combine whatever they have because they want to have a more superior physical chemical properties. Yeah. So for example, they are using activated carbon or ultra filtration. Now, this powder activated carbon used for dissolved organic carbon or micropollutant removal, and sometimes they're also using combination of ozone and ultrafiltration or catalytic membrane reactors, or even using nanofiltration or reverse osmosis brine minimization, using membrane distillation or forward osmosis. Yeah. So for example, here we have a schematic picture of brine minimization and desalination of the geothermal reinjection fluid by the pressure driven membrane. And so we have here geothermal waste process, and we have a membrane over here, and we have a permeate, which is fresh water. And for example, it is used for agriculture field, yeah. And we have like concentrate, and then it rejected again to this one. So it's not being dumped into water. Now, if we compare between several types of filtration, so for example, the microfiltration and ultrafiltration, nanofiltration, reverse osmosis, the driving force are pressure. So, but just because they have like different size of pore, so the ones that can be removed or can be rejected differs. So, for example, the MF or UF particles of pathogen, but then NF, you have organic matter or multivalence ions. As for the reverse osmosis, you also want to remove salt and most organic materials. The energy source is, for example, mechanical or the other. And then the typical flux over here in the liters per meter square per hour is around this value. Yeah. So you can see that, for example, the reverse osmosis has actually lower typical flux. And then the challenge here, for example, for the microfiltration and ultrafiltration is falling, yeah. While this one here for the nano is scaling and organic falling, and then the other one here is requiring a high energy. And then for the forward osmosis, membrane distillation, and the ED here, yeah, the driving force difference, yeah, this is the electrical dialysis. You have here osmotic for the forward osmosis and temperature in the membrane distillation, and you are using electrical in electrodialysis. And they remove, for example, here for the total dissolved solid, non-volatiles, and also ions. And then the energy source here is chemical, thermal, and electrical. And then you can also see that the flux is not too much, yeah. But then you have another challenge here, such as the recovery, the heat loss, or the scaling due to organic falling. So now, after you learn about the membrane, the technology, the process, the design, now we come to the most challenging thing in the membrane, falling. Yeah. So we want to know like what is the falling and what is the mitigation that we can do to it. And you can see this is a STEM picture. Yeah. So the left one is the external fallance. It's the surface of the membrane that you can see something aggregated on the surface of the membrane. While this one here is the cross section. So you kind of freeze the membrane and you split them up, and then you see the cross section. So it's the thickness of the membrane, and you can see that the internal fallance, meaning that they might be stuck in the pore of the membrane. That's even worse. You have so many fallance there. Yeah. So what is the membrane falling? So it's basically a deposition of retained particles or colloids or macromolecules or salt or microorganism on the surface of the membrane or within the membrane, and thus they make or they can cause irreversible flux decline, and they can change the rejection percentage, and they can increase the TMP. And it's actually very costly. Yeah. TMP is transmembrane pressure. It's very costly because it increases energy, like you need to apply more pressure, you need to have a cleaning process frequently, you might also need to change the membrane frequently. That costs money. And if we see this, so for example, this is the black one here is the membrane, and then the red one here is the falling. So this one is the cake layer. We call that as external falling because the person is on the surface of the membrane. There might be some interaction over here, but there is also like internal falling. This is the cross section of the membrane with something stuck in the pore here, and we actually don't want that. And you can see that the external falling over the red one actually hinder the green one in which they should pass the membrane, but now they kind of be hindered by the presence of this falling. So now you can imagine that the rejection becomes smaller, the flux become lower, and actually like there might be like increase of the osmotic pressure over here, which kind of oppose the hydraulic pressure applied for this process. Now, the types of falling itself could be organic, like from the humic substances, proteins, or oil due to adsorption or gel formation. And they can also be inorganic scaling. For example, you have a precipitate of calcium carbonate or calcium sulfate, barium sulfate of silica, and also some probably colloidal or particulate falling, making it silts, clays, metal oxide, and so on. And it can cause pore plugging, making a cake layer on the surface of the membrane. There is also biofouling, like a microbial adhesion, EPS production, biofilm formation. This is most challenging, especially if you are using a membrane that is having a functional group which can be hydrolyzed, like amide, ester, alkoxy, or something like that, because the presence of this microbial might degrade the polymer. Yeah, and then so this is a SAM picture of ultrafiltration membrane. Yeah, it's a hollow fiber.
So the A here is the membrane fold due to the humic acid, and then the B is actually the humic the membrane here. But then after hydraulic backwashing, you practically apply uh, pressure, but the opposite side, you because you want to wash the falling. So now this one here is removed. That's the humic acid is removed, and then the C here is you don't have the falling anymore, but they use backwashing using NaClO. Yeah, and then the D here is a membrane which is filled by another acid. Yeah, and then this one, so this is the falling itself, and this one is also after hydraulic backwashing during using a pressure, and this one is using the NaClO backwashing. So from this data, you can see that there are like two types used here, whether you are using a hydraulic pressure to wash away the falling, or you are using uh, electrolyte solution to wash the falling. Yeah. So the mechanism and factor influence falling is that hydrodynamics, like whether it is cross flow velocity, flux, or turbulence promoters, and it can also be the feed composition, like whether you have natural organic matter or whether you have ion exchange, like so many ions, or pH, or bridging of calcium to gas, and it also influenced by the membrane properties like hydrophilicity, hydrophobicity, roughness, charge, and pore size, and also a concentration polarization on the surface of the membrane, which could exacerbate falling potential. And then the strategy here, we can apply feed pretreatment strategies. Yeah. For example, you have a microfiltration or ultrafiltration pretreatment before the reverse osmosis. It can lower the silt density index to 2.5 or lower, which is superior. Or you can also apply coagulation or flocculation or some filtration or cartridge filters to filters out molecule more than 5 micrometer. And you can also use antiscalant dosing to inhibit crystal growth, as in, for example, you don't want to have a precipitate of ionic compound. And then you can also adjust the pH to prevent the precipitate of calcium carbonate, for example. Or you can also use biocides such as NaOCl, monochloramine to control biofilling, but it must be dechlorinated for polyamide membrane. Yeah. And for the membrane cleaning protocol, so you can have the physical cleaning, backwashing, yeah, forward flush, air scoring, osmotic backwashing using pressure, and you can also have the chemical cleaning using alkaline, acid, oxidizing agent, and so on. Like it depends on which one you want to remove. And then you can also have the clean in place cycles with typical frequency and sequence, or you can have the combination of them. Yeah. And then here, for example, you have a fermentation flux and then filtration time. And then this is the TMP, that is the transmembrane pressure. And then you can see that from the graph, the permeation is actually decreasing over time. If you are using a lower transmembrane pressure, you can see that the way it approaching the asymptote, the equilibrium or the stagnant value becomes even uh, shorter time. Yeah. For example, if you are using higher transmembrane pressure, it reached this one after, let's say, I don't know, 7,000 seconds, for example. So you can also see that the use of higher transmembrane pressure might reduce the falling. And then for the monitoring and control of the biofouling in water system, so because there is it is primarily driven by the nutrients and microbial glue. So there could be assimilable organic carbon limits and also transparent exopolymer particles (TEP). So for example, for the assimilable organic carbon here, which measure the fraction of dissolved organic matter readily available for the bacterial growth. In system like seawater reverse osmosis, the ROC levels above 50 are strongly linked to rapid biofouling. So you kind of check your system and you want to know the AOC value. If it is above 50, it means that in your system it is more prone to falling. And you can also use the transparent exopolymer particles, which are macroscopic sticky gel-like particles made of acidic polysaccharide, which is released by the algae and bacteria. And they actually act as a biological glue or aggregating solid particles, trapping microorganisms, and forming protobiofilms in the water column before they even reach the membrane surface. Now, the early detection for it, for example, there's a pressure drop increase, biofilm sensor, or you actually calculate the ATP measurement. Like you leach the cells, you add a chemical which can bind to the ATP released by the cell, and then it actually emits light, and then you can measure it. Yeah. Now, how to control it? So then you have to keep in mind that about the substrate limitation, you have to know what kind of membrane that you are using, and then compare them to the contents of the feed solution, and also the biocide rotation or sensing disruption. Probably surface modification if you want to, modify the membrane, and also pre-treatment using filtration in like ultrafiltration or microfiltration to reduce the sticky transparent exopolymer particles. So for example, this is the TEP, the gel-like polysaccharide. You have the membrane, you have the TEP layer, you have the TEP in the bulk, and then when they interact with the ions in the pit solution, they might even make cross-link um, transparent exopolymer particles, and then even then it will promote the bacterial growth. So you have like this folding on the surface of the membrane, which actually like forming from different reasons. But anyway, it will degrade or it will decrease the performance of the membrane. Now you want to stop that. So for example, using by increasing hydrophilicity, you introduce the PEG, you introduce the zwitter ionic polymers, or even you coat the polymer using polydopamine, and then you also aim to reduce the roughness, so you kind of aiming for a smoother active layer of the membrane. And probably there's also charge modification to repel the pollen, especially of the concerning ions. And sometimes it is also corporate nanocomposite membrane, yeah, such as titanium oxide, silver, and so on, like graphene oxide, carbon nanotubes, to increase the antimicrobial property. So this is an example of modifying the surface. Um, you have PTFA, you have hydrazine, and you modify one, and you attach another, which is full bistidyl ether, and then you introduce PEG with the malamide modified PEG. So you actually have like a Diels alder over here, and then you can then have a PEG coupled PTFE membrane. But then you can also have a retro Diels alder reaction. So by the time you have your previous PTFE membrane, and then the coating itself will be removed from the membrane. So it's actually one of example using reverse Diels alder reaction to modify the surface of the membrane. The next is examples of the water treatment facilities. So here, for example, we have indirect portable reuse in Orange County, California. And it's actually quite large facility. It's produced up to 130 million gallons per day of purified water. And it provides high quality drinking water for nearly 1 million residents in North and Central Orange County. And the investment itself is quite large, so it's $900 million. And there is also like treatment train, like secondary effluent, micro filtration, reverse osmosis, and also applying UV, peroxide, advanced oxidation, and also injection into ground water basin. Yeah. So in this case, the reverse osmosis here remove pathogens, salts, and also trace of organics, which provide additional barrier. Um, there's actually like I think a video
The
here.
Groundwater Replenishment System, also known as
Um,
GWRS, is a
just to see
trailblazing water
an
reuse
example of
project
a
created
very
through the
large
partnership of the Orange County Water District and
water
Orange County
facility which
Sanitation
can
District.
produce
Located in
130
Fountain
million
Valley,
gallons.
California, the GWRS takes treated wastewater from OC San that would otherwise be discharged to the Pacific Ocean and purifies it using a 3-step process consisting of microfiltration, reverse osmosis, and ultraviolet light with hydrogen peroxide. GWRS water is so pure that minerals are added back in prior to distribution. The result? A new source of water that is superior to all state and federal drinking water standards. The GWRS is the world's largest advanced water purification system for potable reuse. Operational since 2008, the history of this world-renowned facility goes back much further. Water Factory 21, so named because of its pioneering technology from the not yet experienced 21st century.
Okay, I think this is enough to give you an idea that a water facility which provide a lot of water need a very large area of facility with a lot of technology and so on. And then for the I'm going to skip this. This is groundwater replenishment, but it's just the flow when you have the water and then you purify this and you are producing drinking good water. There's also like a small scale here in India using solar powered nanofiltration, which is actually good because the idea is that you're using solar panel to produce energy to support the energy consumption of the system itself. So it is uh, suitable for limited cost. Yeah, and this is very nice. And then there is also like industrial water reuse or in zero liquid discharge. So the main process is that they are doing pretreatment, removing suspended solid, and using reverse osmosis, forward osmosis, and also draw solution recovery. And sometimes they are also using thermal crystallizer, yeah. And then evaporate the remaining water content, and then they have the watering units. As for the membrane distillation crystallization itself, so this is the reactor. So the key fluid streams here, you have a permeate or distillate, which combine clean water streams with high purity for reuse. You have also reverse osmosis concentrate and forward osmosis concentrate, and also solid cake, which is a mixed crystalline chemical salt, which is safe for landfill disposal. So basically, you kind of separate each types of waste in such a way that it is more acceptable for environment. And there is also emerging trends using smart membranes and twins, like using sensor integrated for real-time falling monitoring, machine learning predicting, and also digital twin of the membrane plan for simulation and fault detection. There are also a development of advanced materials like aquaporin-based biomimetic membranes. So basically, you have these kind of pore in which the water can pass through. Yeah. And then there is also like applying materials such as graphene oxide and a 2D material laminates. Yeah. So the difference is that I'm going to this one here is like stride forward aquaporin based biomimetic membranes. That this one here, when you are using a 2D material such as graphene oxide, you can see that the water is actually like coming through like this, like here. Yeah, they have these kind of roots. Yeah, it's like quite different. Or even this, when you have like a stacked graphene or graphene oxide, you have like a layer here, and this is like here the root of the water. That is actually enhance the rejection, enhance the selectivity of the material. So you can imagine that it's like a mixing, a composite of with the organic and inorganic materials. There is also like other using the Maxine and even use the self-assembled block of polymer for precise separation, because we can synthesize the block polymer and then really like want to have a tailor-made membrane like this. Yeah. So the block polymer here, because this is a diblock polymer, they can self-assemble. So they can, have this lamella or this cylinder, and then they can etch. So like we can remove, for example, the red one here, and you can have this morphology or something like this. So it's basically an engineering in the molecular level, because you actually engineer the structure. While this one include molecular organic framework, 2D materials, and so on. Yeah? So you modify the membrane using a more advanced or nanomaterials to combine with the conventional membrane. But you also have to keep in mind that you have to make sure that it's sustainable and promote circular economy, because here the energy, like the development of low pressure, high permeability membrane, reduce energy, and you also want to consider the membrane end of life, like recycling modules, converting to other uses, or developing a biodegradable membranes. And also because if you are having water with high salinity, then you will have like a brine water, a concentrated salt water. Then you might consider using resource recovery, like to get lithium, magnesium, and sodium chloride from desalination brine. And then you can also consider the life cycle assessment comparisons of the membrane plants versus conventional system, just to make sure that you keep in mind, you keep in check the system, whether it support sustainability. And of course there is also challenge and research needs, because you want to have a selective removal of specific micropollutants such as per and polyfluoroalkyl substances such as antibiotics also, without complete demineralization. And you might want to improve the resistance to chemicals such as chlorine and oxidants. Yeah. And you also want to have a robust ceramic or polymeric membranes for a more harsh industrial effluents. And also, when you work with the lab and you want to scale up into a more higher or larger facility, that's also like another problem. Yeah, from laboratory to the scale up, but it creates innovation anyway. And then you also might want to think about the cost reduction for the membranes and module, how to make it, low cost, like everybody can buy it cheaper. So in summary, you have learned about the water pollution, yeah, which is actually complex mixture of many things inside, which require robust barriers so that you can separate them from the water. And then you have learned that the membranes provide a versatile platform covering from microfiltration, reverse osmosis, and also some emerging processes. And also you have learned about the fundamentals in membrane science, such as pore size, solution diffusion, concentration, polarization, and also falling. And you also learn about the process choice depends on water quality goal or energy or cost or falling risk, and also you are expecting to expected to continue innovation in the materials and also system designs, which will improve the sustainability of these water purification process. I think that's it. It's almost 12. Thank you for your attention. If you have any question, you can also ask me. Are there any questions?